Okay, in this video we're going to talk about the Hillshade tool, which is a nice way to visualize elevation data. So here we're using a hypsometric tint to try to visualize the data. We've got a low value of 1,310 meters and a high value of 3,775 meters. This is a nice way to shade it, but what we might want to do is add a hillshade that sort of adds some perception of depth. So we've used the hillshade effect before, which brings out some of that detail. And I'm going to teach you how to calculate the hillshade. So there are lots of examples of tools in here that we're going to use. These two tools are essentially the same. So we'll use the one in 3D Analyst. Our input raster is going to be the data that we downloaded from the national map. So this is elevation data around Colorado Springs at 30-meter resolution, or technically 1/3 arc-second resolution. And we're going to create a hillshade raster of this. The output raster, I'm just going to put in a temp folder for now. Notice that what you're going to be getting is an integer-based raster with a range of 0 to 255. So this is an intensity raster, just a simple brightness value that ranges from 0 to 255. 0 is black, 255 is white. The azimuth option is going to be telling us which direction that our artificial light source is coming from. So this is expressed in positive degrees, 0 to 360. 0 degrees is north, 90 degrees is east. So 315 is the light shining from the northwest. The altitude here is the angle at which that light source is coming in as an angle above the horizon. Ordinarily we think of altitude as being sort of a measurement of height above a datum. So maybe your airplane flies at 30,000 feet. In this case, it's an angular measurement above the horizon. We can model shadows. In this case, this is going to take into account possible, peaks that might obscure valleys and whatnot. Most of the time, we wouldn't do this, but you can add a little bit of detail if you like by modeling those shadows. It tends to take a little bit longer. The Z factor is by far the most important option in here, and the reason for this is that most of the time when you're downloading DEM data, you're going to be downloading data that is probably coming to you in geographic coordinates. So I'm going to cancel out of this for a second. If we go back into the properties of our raster and look at the metadata, the spatial reference is in degrees, and we're pulling this in from the North American datum of 1983. So all of these little grid cells are going to be in decimal degrees, and you can see that down here in the lower right. The reason that this is important is that those are going to be, the height value is given in meters, but the spatial coordinates, the x and the y, are in latitude and longitude. So that's a vastly different distance. So 30-meter resolution, give or take, in the x and y directions, but essentially 1 meter in the vertical direction. So we're going to need to compensate for that. We're going to need to relate our coordinates in the x and y to our coordinates in the z. So we'll put back in our our temporary raster here, and we're going to need to put in a z value. So z value of 1 says that our x and y units and z units are the same unit of measure. If what you're dealing with is decimal degrees in your x and y, then this is definitely not the case. And if we take a look at, if we do a Google search for calculating the z factor, one of the first articles that comes up is a very good one by an Esri cartographer that discusses setting that value correctly. So I highly suggest that you read this article. This is important. What the article recommends is that we can either project the raster or we can input this optional Z factor. It gives you a table of values that are approximately correct. So in this case, if we go back into ARC, we're at about 37 degrees. And so that Z factor would be, give or take, somewhere in this neighborhood. So we've got a Z factor in meters and a Z factor in feet. So we would probably ballpark pick this value, but there are resources around the web that you can use to pick those values precisely. So if we do a quick Google search for Z factor for a raster, there are some tools that are out there that'll help you with this. We've got some more information here, another article, and we can kind of look around at those. The NGA has a website that does this. I think the Navy has another website that does this. Neither of these is really the right way to solve this problem, and we'll talk about that in a second. So we'll go ahead and use this temporary value here, but we're going to we'll put that in here. So you'll notice that this is a very small number. That's because it's a big difference between degrees, which is our x and y, and meters, which is our z. So we'll hit OK. This tool will take a little while to run, depending on the size of your raster. So we'll be back when that finishes. Okay, the Hillshade tool has done its job. We can take a look at the completed version. Most of what we were looking at here is relatively flat, and we've got a bit of a mountainous area up here. If we go back to our original download site from the national map, we get a sort of a hint of this in terms of the overall terrain here. So we'll clear this out and go back to our base map. And we can hide the availability here. You can see that what we've got is just a little bit of the mountain range up here. There's Colorado Springs right at the foothill, and then a relatively flat area with maybe just a little bit peeking in there at the southwest corner. So that's what we've got here on the hillshade. We can zoom in a bit to get a little bit more detail. I'll uncheck the elevation layer underneath. And because this is such a big area, a lot of that detail gets lost. You can see quite a bit more detail when we zoom in. So one of the reasons that this doesn't look very good zoomed out and looks a little bit spotty is because we're probably using a nearest neighbor pyramid to show this at this resolution, and a lot of that detail gets washed out. But once you zoom in a bit, you can see that there is quite a bit of detail in view. These values range from 0 to 254, so nothing apparently reached that 255 value, but ballpark this aligns with what we were talking about in terms of the data structure. It's an integer value that ranges from 0 to 255. In the meantime, I found a nice article, so we'll link to this, but this is another Esri article determining the z value with the equation that you might want to calculate that z-score at any given value. So as we said, this really isn't the right way to solve this problem. The best way to do this is to project the raster. So we're going to do that. So we'll click on Project Raster. We're going to use our original DEM as our input raster. We'll create a temporary projected raster, and we're going to output that in GeoTIFF format, my personal favorite. Erdos Imagine is a pretty good data set. You don't want to use things like JPEG or PNGs to do this because those are really only suitable for images. They don't hold float data very well. So GeoTIFF is a good choice. Erdos Imagine is a good choice. Those would be my recommendations. So for the output coordinate system, we're going to need to choose. And we can do this in a number of different ways. If we're not worried about the how this is going to overlay, you can do something like the World Mercator. Probably more likely what you're going to want is to use the UTM in the local system. So let's take a look at that. So there are a number of different sources to find out the UTM zone of the place that you're interested in. I typically will just do something like a UTM grid zones image search on Google, which usually works out pretty well. If you zoom in on this, you can see that Colorado is right here, so Boulder is going to be within 13. There's some nice shapefile overlays that you can get from the NGA. So NGA UTM zones will take you to shapefiles that you can download and overlay and make it a little easier on yourself. But most of the time, I find just a Google image search works pretty well. So we're going to be projecting into 13 north. So we're going to projected UTM. Because we're working already in an input coordinate system of North America 83, you'll find it easiest to try to stick within that if possible. So I'm going to choose NAT 83 UTM zone 13 north. We won't have to worry about the geographic transformation because we're using the same coordinate system. We can use the sampling technique here is going to make a big difference. So in this case, we don't want to use nearest. We probably want to use something more like bilinear or cubic. We would only use majority if this were sort of a typed data set like land cover. So in this case, we'll choose bilinear, which will probably work fairly well. Cubic would be a little bit smoother, but it's going to take a little bit longer. You can define the registration of this if you want. I'm not going to worry about that, so we'll just hit OK. And that's going to go ahead and reproject that raster into UTM 13 north. And when that's done, we'll be back. Okay, that raster has been reprojected. We have it up here. We're going to take a look at the symbolization really quick. If we zoom out to this layer, this is our reprojected raster. It says decimal degrees down here because our first bit that we loaded was in decimal degrees. But you'll notice that this is looks just a little bit different. So we're going to do the same thing that we did before and calculate a hillshade based on the new raster, the new projected raster. So we'll use the projected raster. We'll put this into a projected hillshade. We'll use the same azimuth and altitude. We're not going to model shadows. This time we can use a Z factor of 1 because our vertical elevation and our horizontal elevation are the same. They're all in meters. So we can hit OK. Oh, file name is incorrect. We'll hit OK, and we'll wait for this to finish. Okay, that hillshade is now done. Notice that we were able to use a Z factor of 1, and what this amounts to is that we're going to have sort of good consistent hillshade drawn across this image. Even when you specify Z factor, one of the errors that you can get is because that Z factor technically changes with latitude. If you're modeling a fairly large area, and in this case this is 1 square degree, which is a fairly large area, you can wind up with some differences in how the shadows are drawn in the northern part versus the southern part. So because Z factor technically does vary, reprojecting your data first is going to guarantee a better result overall. Let's take a quick look at this. So we've got a zoomed in version here. If we get rid of our projected raster and we'll turn on our original hillshade, you'll notice that there's some differences in how this appears. The projected hillshade should be a bit better and have fewer artifacts than this version, which tends to have sort of a an overly contrasted version. So we'll check that back. And in the next example, we'll show you just very quickly what can happen when you don't specify that Z value quickly. Rather, when you don't specify the Z value correctly. Okay, so let's take a look and see what would happen if we tried to do a hillshade without setting the Z value correctly. So we'll use the DEM that's in decimal degrees. We'll set this to output back to that temp folder. We'll leave the azimuth and altitude the same. This time we're going to leave the Z factor at 1. So we'll hit OK. This will take just a minute, so we'll be back when that's complete. Okay, that hillshade has been calculated, and this is the result. What you can see is that this whole thing is a lot darker, a lot darker than the others. So this is the bad hillshade. compared to the normal, much darker. We can zoom out so you can get a picture of what this looks like over the course of the entire degree. It basically looks black, washed out, sort of all of the detail is gone. Not all of it, but most of it. So this is something that you're going to need to be careful of every time you calculate a hillshade, and in fact, the same thing is going to hold true for curvature and slope. So we'll see those in the next video. Stay tuned.